Hello and welcome to the section 3.2 lecture today for Bridges Math Probability. Today we're going to be looking at sort of an advanced topic when it comes to counting the possible outcomes of a situation. We started off with this little sort of explore activity just to try to get a feel for it. What I want you to do, and if you have like a deck of cards, that would be the best. Otherwise, I mean, this could be as simple as put 1, 2, 3, 4 on 4 sheets of paper, even slips of paper, and see how many ways there are to rearrange these. So, kind of the first one we'd look at is there's obviously a difference between ace 3, 6, 5 and ace 3, 5, 6. Just want you to take a look at that. Try to figure out how many, and hopefully a decent way to count them, to figure out how many possibilities there are. So pause the video and give that a shot. Okay, well, if you're back, I hope you actually worked through that. I'm just going to write down, at least for the cards that I have, and you can do the same thing I should have said earlier, right in this area right here. And so I'll go ahead and write that. I can put it there. So I had ace 3, 6, and 5, 5 and 6. And as far as trying to be organized, I tried kind of keeping everything the same for as long as I could. So I'm trying to keep an ace in the first spot and a 3 in the second spot. But right now I'm obviously out of options for that, so I need to change up what's in the second spot. So I'm going to put a 5 there, 3, 6, ace 5, 6, 3. And I kind of notice that every time I switch what's in the second spot, I get 2 more options from switching the order of the ones in the third and fourth spots. Then I'll get ace 6, 3, 5, and ace 6, 5, 3. Those are all the options with aces. Moving forward, I'll go ahead and put something else in that first spot. Maybe I have 3 ace 5, 6, 3 ace 6, 5, 3, 5 ace 6, 3, 5, 6 ace. Let's see, sorry, 3, 6 ace 5, and 3, 6, 5 ace. Those are all the options that start with a 3. Now I bump to the 5s. Ace 3, 6, ace 6, 3, 3 ace 6, 3, 6 ace, 6 ace 3, and 5, 6, 3 ace. Then lastly, the last thing I need to start with is the 6. And without too much, I mean, you probably saw it happening already, but every one of these I'm getting 6 options for. Okay, so 6 ace 5, 3, 6, 3 ace 5, 6, 3, 5 ace, 6, 3, oh, I'm out of 6 3s. Oops. 6, 5 ace 3, and 6, 5, 3 ace. Okay, so all in all, that gives me 24 different ways that I can arrange these 4 cards. And obviously, it's a little bit time consuming. I mean, I spent the better part of a couple minutes doing that. And I guess, would you be surprised to know that there's a mathy way to do that? Well, we can decide it by the card placement, sort of the position in the lineup, and we can look at it that way. When I'm picking what the first card is, I have 4 options. It could have been any of the cards. Once I take that option off the table, it's no longer possible to show up again because I only had 4 cards in my hand. So once I put let's say the ace down, now I only have the 3, 5, and 6. So the second one has 3 options. The third one has 2 options, and the last one has 1 option. We've actually looked at this before as just the fundamental counting principle, saying that the number of possibilities of things that can happen are the product of the things that can happen at every stage. Okay, and it happens that 4 times 3 times 2 times 1 is 24. So not too surprising. We're going to get a little bit more involved with ideas like that as we go here, so let's not stress out about it too much yet. A permutation, that's what we just did, is an arrangement of, I'm going to be a little bit specific with the definition so that I get some variables taken care of. N, no, I'm going to write R, no, let's stick with N, of N total items into R open spots. Okay, the way the question was phrased before was that we had 4 cards to choose from, and I just wanted you to arrange them in some order. So really, that's 4 cards taken into 4 total spots, into 4 open spots, sorry. If I would have changed my mind and said, well, let's say you've got 4 cards, but I want you to arrange 2 of them, give me a layout for 2 of them, then the question's quite a bit different. And we want to be able to have an easy way to determine either one of those. Okay. So the notation for this, for a permutation, so specifically in what we did, we said we had 4 items, and it was a permutation, so we used the letter P into 4 spots. So we've kind of got 2 what we call subscripts, writing it below the main line as a subscript, and exponent as a superscript because it's up above. But this is writing it in subscript. So I've seen it this way where it's NPR, and that's the one that I'm going to use most often. I've also noticed that sometimes people go this way or this way. And that's the N there. And that's the R. Or even, this is the other more common one. Kind of for writing in bigger papers, things where you don't want things to take up more than one line, like math research papers would probably do it that way because it doesn't adjust the line spacing at all. But as I said, I'm going to use this one more often than anything else. The formula for it is, I'm going to write it and then talk about it. Okay. It's what we call, and so I have it right here, what is an exclamation point? Is that just an excited N? No, it's not. It's actually a math symbol, and it does mean something very, very specific. It means factorial. So n exclamation point is written as, or not written, but said as n factorial. Okay, and n factorial is equal to, well, it starts off with n, and technically I think deep down it starts somewhere else, but whenever we do it, we always start with n, just because we already see that number, so we're going to put that number there. and then n minus 1, so the number just below n minus 2, the number just below that, and it's a string of multiplication all the way down to 1. Okay, so it's a string of multiplication all the way down to 1. Now, there's one thing that's kind of weird. If I look at what we did, I claim that we, so another way that this statement is read is people rarely actually say permutation, but you can. A permutation of 4 items, the total number of items, taken 4 at a time is another way that they'll say that. That doesn't intuitively help me that much. Okay, I think of it as I have 4 total items, and as I wrote up above, I have 4 spots to put them in. Okay, that part makes a little more sense to me. Now the issue with this is this right here. If we follow the formula, it's n factorial, it's 4 factorial. Again, this one's n and this one's r, over n minus r factorial. But as we look at it, and I can even write this out, 4, 3, 2, and 1. But as we figure this part out, 4 minus 4 is 0. So what is 0 factorial? And we would always want to say, well, 0 factorial is 0. It's kind of the way we think of it. But let me throw something else out there. Let's do some calculations with factorials, just for a minute. Let me find some open space here. Let's look at some different factorials, which we're going to end up doing some of the problems that we have assigned to us, but that's okay. I think that's good practice. Let's go to 5 factorial. Let's figure all these out. And actually, I'm going to grab all these. Nope, don't do it that way. Let me just drag them down a little bit. So, 1 factorial, well, it's 1. It's 1 times, well, I hit 1, so I stop. And that was kind of my rule, is that I started with my number, and I decreased my way down to 1. This one starts at 1, so I think we're good. 2 factorial is 2 times 1. Okay, I can get on board with that. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1. And so I think we can do some calculations here. 2 times 1 is 2. 3 times 2 is 6 times 1 is 6. 4 times 3 is 12 times 2 is 24. And times 1 is 24. And then 5 times 4 is 20. 3 times 2 is 6. 6 times 20 is 120. Now let me ask you this, because our goal is to figure out what is 0 factorial, especially if we make the claim that it's not 0. How do we get from here to here? Now that's not entirely obvious, but this list has a 5 and then 4, 3, 2, 1. This one has 4, 3, 2, 1. So I actually get between those two by dividing them by 5. And then 24 to 6, that sounds like divide by 4. 6 to 2 is divided by 3. 2 to 1 is divided by 2. And so if I repeat that pattern, I should divide by 1. And so 0 factorial would also be 1. Just another reasoning behind it. It's kind of like the rule that we all should know, anything to the 0 power is equal to 1. It's similar to that. Okay. So we want to make a note of that, though. And I'm going to put it right here. And I'm going to put a star by it. 0 factorial, oops, that's a 1. 0 factorial is always equal to 1. Okay? You don't want to forget that. Another way you can think of it is the factorial is the way to arrange, any n factorial is the way to arrange n items in a row. Well, how many ways are there to arrange 0 items? Some people would argue that it's 0. I'm gonna, be the devil's advocate and say, you can arrange it one way. You can not do it. Okay, just like when you take your next test, you can say, well, I can do it one way. I can not do it, and then okay, I can give you the 0, not 0 factorial. So if we go back to this that we were working on, it turns out that 4 times 3 times 2 times 1 is 24, and divided by 1 just ends up with 24. So we didn't really do this permutation formula, but we kind of did. Okay, we kind of did. So let's take a look at a couple other factorials, maybe some that we haven't done yet. Okay, we did that one. It's 6. Actually, let me write it out. Why not? 3 factorial, 3 times 2 times 1, which is 6. 5 factorial, 5 times 4 times 3, 2, 1. We said that was 120. Now to get to 7 factorial, I could just figure it out. It's going to be a little bit painful, but I also want to clue you into maybe the use of a calculator. Because even as bad as I would say my calculator is, it doesn't have that many functions. It itself has a factorial button right there. And even when I hit it, it says fact 7 or factorial of 7 is 5040. It's going to work on most calculators, even your, say, phone calculators. You might have to turn it sideways, but I'll bet it's on there. Let's figure out a few permutations. So we want to follow the formula that's right up here. 5 factorial over 5 minus 3 factorial. Now here's a trick. It's a little early to bring this up, but I think it's okay. I know that 5 minus 3 is 2, so this is going to be 2 factorial. Now, I want to write this out once, and I don't want to write it out every time. I know that seems kind of lazy, but I'm okay with it. If I look at this, 5 times 4 times 3 times 2 times 1 divided by 2 times 1, the 2 cancels and the 1 cancels. Not that that really matters. In fact, in any of these permutations, or what we're going to look at next, even though like the fraction is a big part of it, your answer is never going to be a fraction. Not even an improper fraction, not even a mixed number. Okay, there's not going to be any decimal part to this. Because let's think about what we're doing. We're counting the number of outcomes that happen in a given situation. We're finding the number of arrangements of 4 cards that I can give. And that's not going to be a fraction. I'm not going to have 13 and a half ways to move cards around. So no matter what, we're always going to get a whole number. That's kind of the nice part. So always look to cancel your fractions. Cancel something in your fractions. 5 times 4 is 20, times 3 is 60. So we get 60 for a list of 5 things arranged in groups of 3. Now the reason I said there's kind of a shorthand to this, or not really a shorthand, but I would say a shortcut, is I don't always want to write this top one all the way out to 1. And I don't need to. Because something cancels, it's nice to not have to write as much. I know that 7 minus 3 is going to be 4. So I'm going to write this 7 factorial. Okay, well, I've got to write the numbers in order, I guess. That would help. 7 times 6 times 5. Since I know the bottom is 4 factorial, I'm going to write this as 4 factorial and accept that those two are going to cancel out. Just a little bit of shorthand just to save you a little bit. Okay, but that's gonna cut a lot off your writing. Let's see, how can I do this? 6 times 5 is 30, and 30 times 7 is 210. Next one, I have 10 factorial over 10 minus 7 factorial. So inherently, what I end up kind of doing is I kind of deal with the denominator first. So I see how far I have to write this out. 10 minus 7 is 3. So sadly, I still have to write this out a ways. And the 3 factorials will cancel, but I still have a lot of work to do. Grab a calculator. And I get 604,800. Okay, let's move on. We've already seen that. Let's take a look at some examples. So here it says the license plate begins with 3 letters. If the possible letters are A, B, C, D, and E, how many different permutations of these letters can be made if no letter is used more than once? Okay, I like to look at this in 2 different ways. Okay, because I feel like, yes, formulas are important, but if I can figure it out quicker without it, why wouldn't I? So let's think about the reasoning side of it first, and maybe later we'll switch up the order. So I have 3 letters that I need to fill in, and I have A, B, C, D, and E. So for the first one, I have 5 options. For the second one, 4, and for the third one, 3. If I multiply those together, I'm going to get 60. So I should have 60 possibilities. Let's look if that verifies with the formula. In the formula, I have a group of 5 things, and I want to arrange 3 of them. Well, we've actually done this already. 5 factorial over 5 minus 3 factorial. If I look at the bottom first, that's 2 factorial. So 5 times 4 times 3 times 2 factorial, and those cancel. I get my 5 times 4 times 3, which is 60. On the next one, I have a school club. In a school club, a president, vice president, and secretary must be selected among 7 candidates. How many ways are there to do that? Let's look at the formula first. So I have 7 candidates, and I have 1, 2, 3 different positions to fill. So that's 7 things into groups of 3. 7 factorial, another one that we've also already done. 7 minus 3 is 4, so 7 times 6 times 5 times 4 factorial. The 4 factorials cancel, and I get 7 times 6 times 5, which is 210. In the using just the counting principle or reasoning, the math works the same. I have 7 options for the president. For the vice president, I have 6 options left. And for the secretary, I have 5 options after that. And 7 times 6 times 5 gives me that 210. Now I want you to think about this. What if they decided to also select a treasurer? Are the number of ways going to go up or go down? And I want you to put your guess right here. Okay, I think it's good to take guesses on things because we don't really know what's going to happen. Maybe we do. I don't know. Because we're going to see a lot of the same numbers. But this time I want to take them in groups of 4. So we have 7 factorial over 7 minus 4 factorial. The bottom is going to end up being 3 factorial. So the top has to be 7 times 6. I keep wanting to do that. Times 5 times 4 times 3 factorial. I keep wanting to write 5 after 7. The 3 factorials cancel. And in fact, there's 4 times as many options on this. So if you said go up, you were right. Because the denominator got smaller by a factor of 4. So multiplying this by 4, I get 840. Now I'm going to talk about this last one, this last set of problems, but this is kind of going to be the extent that I talk about it, other than referencing it next time. I'm not going to put any questions like this on the test because it's such an isolated concept that I'm not the biggest fan. I almost wish I wouldn't have put it on there, but now that I put it on there, I feel like I have to do it. So let's take a look. Not too bad to start. How many ways can I rearrange the letters in the following words? And the way that they're written is one that counts. So anytime I want to rearrange everything, I'm looking at the number of ways to permute all the things that I have. So this is our 4p4. Which happens to be 24 that we saw with the cards and with the multiple times that we talked about that one. So I don't feel like I need to talk about that one again. This one has 6 letters, and I want to arrange that 6 ways. It's going to be 6 factorial over 6 minus 6 factorial, which 6 minus 6 ends up being 0, so it's 1. So this is just 6 factorial, which we didn't actually figure out. I encourage you to double check that it's 720. Now the last one is really the one that I kind of am saying that I don't really want to bring up again. It's such an isolated thing. There's a repeated letter in there. Technically, what we have to do anytime we come across a word that has repeated letters, okay? Most of the time, we're not actually using permutations. We're just using the factorial. So what we really want to do is we want to say, well, there's 5 letters, and in every one of these problems, if we just use factorial, we would still have to do this also. I'm just not the biggest fan of showing it because it's kind of, like I said, kind of bridging a gap between what we're talking about now and what we're going to talk about. But it's neither really in one side or really in the other side. So what we would need to do is we would say, well, it's 1 factorial because the A is repeated once. It's 2 factorial because there's 2 P's. It's 1 factorial for the 1L and 1 factorial for the 1E. Whatever we put on the bottom is a way to get rid of options where anytime we have those 2 P's in opposite locations. Okay? And if like we're going to get Apple, we're also, if we go through our entire list, we're going to get Apple again, but where the 2 P's have switched positions. And the problem is we can't tell the difference between those, so they're not really different permutations. They're not different arrangements. Okay? And we would do this for every one of these. For number, we would do 6 factorial over 1 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial. As much of a pain as that is. Okay? In this one, it happens to be that we take 5 factorial, which double check that that's 120. And we would divide it by 2. Because that's 1, that's 2, that's 1, and that's 1. So 2 is on the bottom, so there's 60 different ways. Like I said, we're going to talk about it there and just kind of leave it. You don't have any problems about those. It's just another thing that you can do. All right, so get those problems at the bottom done. Otherwise, I hope you have a great day. Let me know if you have any questions, and we will see you in class.